February 25th, 1945, Ibaraki Prefecture, Japan. Rice paddies stretched endlessly under gray winter skies when the sound of twisted metal and engine failure shattered the silence. Marine Second Lieutenant Donald Carlson's F4U Corsair, Bureau number 57251, lay crumpled but intact in the mud. For the Japanese Navy engineers who would soon examine this machine, it represented hope. Finally, they had captured America's most feared carrier fighter completely undamaged. At Yokosuka Naval Arsenal, Lieutenant Suetsu Nomura and his team believed they held the key to closing the performance gap that was destroying Japanese aviation. Panel by panel, rivet by rivet, they began tearing apart the Corsair's secrets. The Pratt & Whitney double Wasp engine, the distinctive bent wing design, the structural steel that somehow balanced impossible strength with surprising lightness. Every measurement was recorded, every alloy analyzed, every weld cataloged with scientific precision. But as the weeks passed, a horrifying realization began to dawn on the Japanese engineers. They had expected to find blueprints for victory. Instead, they discovered something far more terrifying than any enemy aircraft design. The wreckage lay scattered across the frozen rice paddies like pieces of a deadly puzzle waiting to be solved. Bureau number 57251 had traveled 8,000 miles from Vaught's Connecticut factory, through Pacific carrier decks and countless combat sorties, only to end its war in the mud of Ibaraki Prefecture. The F4U Corsair's distinctive inverted gull wings jutted skyward at unnatural angles, but the fuselage remained largely intact, a stroke of fortune that would soon transform Japanese naval aviation's understanding of just how far behind they had fallen. Lieutenant Suetsu Nomura received the telephone call at Yokosuka Naval Arsenal at 0600 hours on February 26th. The voice on the other end carried barely contained excitement. An American Corsair had force-landed with minimal structural damage. For the first time in the Pacific War, Japanese engineers would have access to a complete specimen of the fighter that had been systematically destroying their air forces across the Pacific. Nomura set down his morning tea and reached for his technical notebook. This could be the breakthrough they desperately needed. Within hours, recovery teams had loaded the Corsair onto flatbed trucks for transport to the first Naval Air Technical Research Arsenal. The bent-wing fighter arrived at Yokosuka like a technological time capsule from America's industrial heartland. Engineers gathered around the aircraft in the cold morning air, their breath visible as they circled the machine that had terrorized Japanese pilots for months. The Corsair's blue-gray paint bore the scars of Pacific combat, bullet holes patched with aluminum plates, oil stains that spoke of countless carrier landings, and the weathered look of a machine built for war. Nomura's team began their preliminary examination with the methodical precision that had made Yokosuka Arsenal renowned throughout the Imperial Navy. They measured the propeller diameter, 13 feet, 3 inches of Hamilton Standard constant speed efficiency that dwarfed anything in Japanese service. The Pratt & Whitney R2800 double Wasp engine dominated the forward fuselage, its 18 cylinders promising power levels that Japanese manufacturers could only dream of achieving. Early estimates suggested output approaching 2,000 horsepower, nearly double what most Japanese fighters could produce. But it was the airframe construction that first hinted at the magnitude of what they faced. As teams removed inspection panels and began cataloging structural details, patterns emerged that challenged fundamental assumptions about aircraft design. The Corsair's framework combined welded steel tubing with riveted aluminum panels in ways that seemed to defy conventional engineering wisdom. Load-bearing members appeared over-engineered by Japanese standards, yet the overall weight remained surprisingly manageable. The Americans had somehow achieved structural integrity that Japanese designers thought impossible without massive weight penalties. The initial excitement that had electrified the arsenal began to give way to something approaching unease. Commander Iwaya, overseeing the foreign technology section, watched his engineers work with growing concern. Their preliminary reports described construction techniques that pushed beyond current Japanese manufacturing capabilities. The rivet patterns alone required precision tooling that most Japanese factories could no longer guarantee in 1945's increasingly desperate industrial environment. 3 weeks into the disassembly process, Nomura made a discovery that would fundamentally alter their understanding of American design philosophy. Removing panels from the Corsair's outer wing sections, he expected to find the all-metal construction typical of modern fighters. Instead, he discovered fabric-covered surfaces on portions of the wing's trailing edges. For a moment, Nomura wondered if this represented some American manufacturing shortcut, a sign that even Vought was struggling with material shortages. Further investigation revealed the truth to be far more sophisticated. The fabric covering was not a compromise, but a deliberate weight-saving measure that demonstrated American designers' willingness to employ mixed material construction where optimal. The fabric sections were precisely engineered, using techniques that required manufacturing tolerances Japanese industry could no longer achieve. What had initially appeared to be a sign of American limitation instead revealed a level of design confidence the Japanese engineers found deeply unsettling. As winter gave way to spring, the Corsair's secrets continued to unfold in ways that challenged every assumption about aircraft construction. The engine mount system employed vibration-damping techniques unknown in Japanese practice. The landing gear retraction mechanism achieved strength-to-weight ratios that seemed impossible using conventional materials. Most disturbing of all, the quality control evident throughout the airframe suggested manufacturing standards that required industrial infrastructure Japan simply no longer possessed. Lieutenant Toyota, responsible for field recovery operations, had been present when the Corsair was first examined in the rice paddy. He had expected to find an aircraft similar in basic construction to Japanese fighters. Perhaps more powerful, certainly better equipped, but fundamentally built using familiar techniques. Instead, the Corsair revealed itself as a product of an entirely different industrial philosophy. Where Japanese designers had learned to accept compromises imposed by material shortages and manufacturing limitations, American engineers appeared to have enjoyed unlimited access to advanced alloys and precision tooling. The psychological impact on the engineering teams began to manifest in subtle ways. Progress reports that had initially bubbled with enthusiasm took on increasingly technical, almost clinical tones. Engineers who had expected to spend weeks extracting American design secrets instead found themselves confronting the sobering reality that secrets alone would not be enough. The Corsair was not simply a better airplane, it was the product of a manufacturing ecosystem that Japan could no longer match. By April, internal memoranda began acknowledging what nobody wanted to say directly. Replication would be impossible under current conditions. The captured Corsair had revealed not just American technical capabilities, but the vast industrial gulf that separated the two nations. Japan's factories, already struggling with material shortages and bombing disruptions, lacked the precision machinery necessary to duplicate the Corsair's critical components. Even if they possessed complete manufacturing drawings, the airplane would remain beyond their reach. The irony was inescapable. For months, Japanese pilots had reported that American fighters seemed almost supernaturally robust, capable of absorbing tremendous battle damage and still returning to their carriers. The captured Corsair explained why. It had been built using industrial techniques and material specifications that treated durability not as a luxury, but as a basic design requirement. The Americans could afford to over-engineer their aircraft because their factories possessed the capacity to manufacture precision components at unprecedented scales. Nomura's final report on the Corsair's preliminary examination would become a classified document that few beyond Yokosuka's senior staff would ever read. In careful, understated language, it acknowledged that Japanese aviation faced challenges that transcended mere technical problems. The captured fighter had provided answers, but not the ones they had hoped to find. Instead of revealing a path to competitive parity, it had illuminated the true scope of Japan's industrial disadvantage. The Corsair represented more than American engineering skill. It embodied the manufacturing might of a nation whose industrial base remained untouched by war's destruction. Spring arrived at Yokosuka Naval Arsenal with the methodical rhythm of disassembly. 10 officers and 10 civilian designers worked alongside 150 enlisted personnel from the Foreign Technology section, transforming the captured Corsair from complete aircraft into thousands of individually cataloged components. The hangar that housed Bureau number 57251 had become a shrine to reverse engineering, its concrete floor mapped with chalk outlines, showing where each panel, bracket, and structural member belonged in the grand puzzle of American aviation technology. Nomura supervised the operation with the precision of a surgeon, ensuring that every rivet removal was photographed, every weld joint measured, and every material sample prepared for metallurgical analysis. The team had salvaged additional components from other crashed Corsairs scattered across the Pacific Theater, creating a composite understanding of F4U construction that represented months of painstaking fieldwork. Each piece told part of a larger story about American manufacturing capabilities that grew more sobering with every measurement. The Pratt & Whitney double WASP engine commanded the central workspace, its 18 cylinders arranged in two banks that promised power levels approaching 2,450 horsepower in later variants. Japanese engineers had never seen an aircraft engine of such complexity operating with such apparent reliability. The supercharger assembly alone contained precision machined components that would have challenged Japan's best factories under peacetime conditions. In the increasingly desperate circumstances of 1945, with Allied bombing disrupting tool and die production, such precision had become essentially impossible to achieve. Lieutenant Toyoda's field reports provided crucial context for the technical discoveries. His teams had recovered Corsairs from crash sites across the Pacific, documenting battle damage that revealed the aircraft's extraordinary structural resilience. One F4U had returned to its carrier with over 200 bullet holes, its port wing root damaged by cannon fire and hydraulic lines severed, yet the pilot had landed successfully. Another had absorbed a direct hit from anti-aircraft fire that destroyed half its elevator surface, but the remaining control authority proved sufficient for carrier recovery. The pattern was unmistakable. American designers had built survival into every structural element. As teams stripped away the Corsair's aluminum skin panels, the underlying framework revealed construction techniques that challenged Japanese understanding of weight-efficient design. The fuselage employed a semi-monocoque structure that distributed loads through the skin itself, rather than relying entirely on internal framework. This approach required manufacturing precision that exceeded Japanese capabilities, but it achieved structural strength that traditional methods could not match. More disturbing still, the Americans had implemented these techniques as standard production procedures rather than experimental innovations. The fabric-covered wing panels continued to perplex the engineering teams. Initial assumptions that this represented American material conservation proved entirely wrong upon detailed examination. The fabric sections were integrated into the wing's structural design with sophisticated engineering that demonstrated complete confidence in mixed material construction. Japanese designers, constrained by material shortages and simplified manufacturing requirements, had never attempted such complex integration. The Americans appeared to view design optimization as a routine engineering challenge rather than an emergency expedient. Metallurgical analysis of the Corsair's structural components revealed alloy compositions that Japanese industry could no longer reliably produce. The aluminum-magnesium framework employed material specifications that required consistent quality control throughout the supply chain. By mid-1945, Japanese foundries struggled to maintain even basic alloy standards. Bauxite imports had been disrupted by submarine warfare, magnesium supplies had dwindled due to Allied bombing of production facilities, and the skilled workers who understood advanced metallurgy had been drafted for military service or relocated to higher priority weapons programs. Commander Iwaya reviewed progress reports with growing concern about their implications for Japanese aviation. The engineering teams were methodically documenting their inability to replicate American manufacturing techniques under current conditions. Tool and die shortages meant that rivet holes could not be drilled to the tolerances required for optimal structural integrity. Heat treatment facilities lacked the precision temperature control necessary for proper alloy strengthening. Quality inspection procedures had been simplified to accommodate increased production demands, but the Corsair's construction required quality standards that Japanese factories could no longer guarantee. The captured aircraft's wing design presented particularly intractable challenges. The distinctive inverted gull configuration was not merely aesthetic, it solved complex engineering problems related to propeller clearance, landing gear retraction, and structural load distribution. Replicating the wing would require manufacturing techniques that integrated multiple engineering disciplines into a single production process. Japanese factories had been forced to simplify their procedures as the war progressed, but the Corsair's wing demanded manufacturing complexity that exceeded their current capabilities. Production data obtained from other captured American equipment painted an even more sobering picture. United States factories had manufactured over 12,000 F4Us by war's end, achieving production rates that dwarfed Japanese aircraft manufacturing even during peak periods. The Americans had industrialized precision manufacturing to degrees that Japanese planners had not thought possible. While Japanese factories struggled to produce dozens of fighters per month using simplified construction techniques, American plants delivered hundreds of Corsairs built to specifications that Japanese industry considered impossible to achieve at scale. By late spring, internal memoranda began acknowledging what the engineering teams had discovered through months of detailed analysis. Japan's manufacturing base had eroded to the point where even complete technical drawings would not enable Corsair replication. The aircraft represented not just American design capability, but the industrial infrastructure of a nation whose manufacturing capacity had expanded rather than contracted during wartime. Japanese factories, meanwhile, had been forced to accept wider rivet spacing, reduced alloy quality, and simplified assembly procedures just to maintain minimal production levels. The psychological impact on the engineering teams became increasingly evident as their work progressed. Reports that had begun with optimistic assessments of American technical approaches gradually evolved into clinical documentation of Japanese industrial limitations. Engineers who had expected to extract competitive advantages from the captured aircraft instead found themselves cataloging the extent of their nation's manufacturing disadvantage. The Corsair had become a mirror reflecting Japan's industrial decline rather than a pathway to technological recovery. Nomura's detailed analysis of the wing spar network provided perhaps the most definitive example of the challenges they faced. The Corsair employed boxed spars that achieved optimal strength-to-weight ratios through precise manufacturing tolerances and advanced alloy compositions. Replicating this design would require tooling precision that Japanese factories could no longer maintain and materials quality that supply disruptions had made impossible to guarantee. Even if they reverted to simpler construction techniques, the resulting aircraft would sacrifice approximately 15% of the original's energy absorption capability, a potentially fatal compromise in combat conditions. The spring's work had transformed the captured Corsair from a symbol of hope into evidence of an insurmountable industrial gap. Japanese engineers possessed the technical knowledge to understand American design innovations, but they lacked the manufacturing infrastructure necessary to implement them. The aircraft that had promised to reveal American secrets had instead illuminated the true scope of Japan's strategic predicament. Victory would require not just superior tactics or enhanced pilot training, but industrial capabilities that no longer existed within the Japanese Empire. The revelation struck Nomura with the force of a physical blow as he reviewed the final metallurgical reports in his cramped office overlooking Tokyo Bay. The numbers told a story that no amount of tactical brilliance could overcome. Japan's aluminum-magnesium alloy production had collapsed by 40% since 1943, while the captured Corsair required material specifications that exceeded even peacetime Japanese manufacturing standards. The engineering teams had spent months documenting American technical innovations, only to discover that innovation alone meant nothing without the industrial capacity to implement it. The strategic materials crisis had been developing for months, but the Corsair analysis brought its implications into sharp focus. Allied submarines had systematically targeted bauxite shipments from the Dutch East Indies, reducing the raw materials essential for aircraft-grade aluminum production. Magnesium supplies, already constrained by limited domestic production, had been further disrupted by Allied bombing of chemical processing facilities. Even if Japanese engineers could replicate every aspect of the Corsair's design, they lacked access to the fundamental materials required for construction. Lieutenant Toyoda's field reports provided devastating context for the supply chain failures. Recovery teams had documented Corsairs that had sustained battle damage which would have destroyed any Japanese aircraft, yet continued flying and returned to their carriers. One F4U had absorbed cannon fire that severed its starboard aileron control cables and damaged its wing spar, but the aircraft's structural redundancy allowed the pilot to maintain control using trim tabs and differential throttle. Japanese fighters, built with minimal material margins due to supply constraints, possessed no such damage tolerance. The manufacturing tolerances revealed in the Corsair's construction highlighted the gulf between American and Japanese industrial capabilities. Rivet holes in the F4U's aluminum panels were drilled to specifications that varied by less than 5/1000ths of an inch, precision that required tooling and quality control procedures that Japanese factories could no longer maintain. Allied bombing had destroyed much of Japan's precision machinery, while the skilled technicians who operated such equipment had been conscripted for military service or reassigned to higher priority weapons programs. Commander Iwaya's staff meetings had taken on an increasingly somber tone as the implications of their analysis became clear. Production reports from Japanese aircraft manufacturers painted a picture of systematic decline that made Corsair replication impossible regardless of technical knowledge. Kawasaki's monthly fighter output had dropped from over 200 units in 1943 to fewer than 60 by spring 1945. Nakajima faced similar constraints, with quality control failures reaching levels that would have been unacceptable in peacetime production. The captured aircraft's engine presented perhaps the most intractable challenge. The Pratt & Whitney Double Wasp represented manufacturing sophistication that Japanese industry had never achieved, even during optimal conditions. Its precision machined cylinders required metallurgical consistency that Japanese foundries could not guarantee with disrupted supply chains and improvised materials. The supercharger assembly alone contained components that would have challenged Japan's most advanced machine shops under peacetime conditions. In the chaos of 1945, such precision had become impossible. Comparative analysis with Japanese fighter designs revealed the extent of the performance gap. The Kawasaki Ki-100, among Japan's most capable late-war fighters, employed simplified construction techniques necessitated by material shortages and manufacturing constraints. Its engine produced approximately 1,200 horsepower, roughly half the Corsair's output, while its airframe lacked the structural redundancy that allowed American fighters to absorb tremendous battle damage and continue flying. Japanese pilots reported that Allied fighters seemed almost supernatural in their ability to survive combat encounters that would have been fatal to Japanese aircraft. The production numbers told an even more sobering story. American factories had manufactured thousands of Corsairs using assembly line techniques that treated precision as a routine requirement rather than an exceptional achievement. Vaught's Connecticut facility alone had produced over 4,000 F4Us by war's end, while Goodyear and Brewster contributed additional thousands under license agreements. Japanese aircraft production in 1945, meanwhile, had fallen to monthly rates measured in dozens rather than hundreds, using construction techniques that had been simplified to accommodate degraded manufacturing capabilities. Quality control had become a particular source of frustration for Japanese engineers examining the Corsair's construction. American factories maintained inspection standards that ensured consistent performance across thousands of aircraft, while Japanese production facilities had been forced to accept wider tolerances and reduce specifications just to maintain minimal output levels. The captured F4U represented manufacturing consistency that Japanese industry could no longer achieve, every rivet properly installed, every weld meeting specification, every component manufactured to tolerances that Japanese factories now considered impossible. The strategics, implications extended beyond individual aircraft performance to entire operational concepts. American carrier aviation depended on aircraft that could absorb battle damage and return for repair, enabling continuous operations over extended periods. Japanese fighters, built with minimal structural margins, required replacement after relatively minor combat damage. This difference in durability translated into operational advantages that compounded over time. American carriers could maintain higher sortie rates because their aircraft survived longer in combat conditions. Fuel quality presented another insurmountable obstacle to Corsair replication. The F4U's high-performance engine required aviation gasoline with octane ratings that Japanese refineries could not produce in sufficient quantities. American factories designed their aircraft, assuming access to high-octane fuel as a standard resource, while Japanese engineers had been forced to adapt their designs to accommodate increasingly low-quality aviation fuel as refining capabilities deteriorated under Allied bombing. The captured aircraft's maintenance requirements highlighted yet another aspect of the industrial gap. Corsairs were designed for carrier operations that demanded reliability under harsh conditions, salt spray, temperature extremes, and the constant vibration of shipboard life. This required materials and manufacturing techniques that prioritized durability over cost considerations. Japanese aircraft, built under severe resource constraints, lacked such margins and required more frequent maintenance using parts that were increasingly difficult to obtain. By summer 1945, the engineering team's final assessments acknowledged what months of analysis had revealed. Capturing American technology meant nothing without the industrial infrastructure to implement it. The Corsair represented not just superior design, but an entire manufacturing ecosystem that Japan had never possessed and could not hope to replicate under wartime conditions. American factories treated precision manufacturing as a solved problem, while Japanese industry struggled to maintain even basic production capabilities. The psychological impact on the engineering teams had evolved from initial optimism through growing concern to something approaching despair. They had hoped to find technical solutions that could offset Japan's industrial disadvantages, but the Corsair analysis revealed that no amount of engineering cleverness could compensate for fundamental manufacturing limitations. The aircraft had become a symbol not of American innovation, but of Japanese industrial collapse. A reminder that modern warfare required not just tactical skill, but industrial capacity that Japan no longer possessed. Nomura's final report would conclude with stark honesty. They could measure every component, analyze every design decision, and document every manufacturing technique, but replication remained impossible under current conditions. The captured Corsair had provided complete technical knowledge while simultaneously proving that knowledge alone was insufficient. Victory required industrial capabilities that no longer existed within the Japanese Empire. The realization that full replication was impossible forced Commander Iwaya to confront a different question. What lessons could be extracted and applied within Japan's diminished capabilities? If Japanese industry could not match American manufacturing standards, perhaps Japanese doctrine could adapt to exploit whatever advantages remained possible. The captured Corsair would serve not as a blueprint for construction, but as a guide for tactical evolution in the war's desperate final phase. Intelligence officers studying the F4U's combat performance data had documented dive speeds exceeding 400 miles per hour from altitudes above 30,000 feet. This capability fundamentally altered interception calculations for Japanese fighter pilots, who had trained under the assumption that diving attacks could be anticipated and countered through superior climb rates and maneuverability. The Corsair's ability to maintain structural integrity during high-speed dives while retaining control authority for recovery meant that American pilots could initiate attacks from previously impossible angles and altitudes. Nomura's team developed training materials based on their structural analysis, creating diagrams that illustrated the Corsair's damage tolerance under various combat conditions. Japanese pilots needed to understand that the aircraft they faced could absorb punishment that would destroy any Japanese fighter and continue operating effectively. One captured pilot had reported that his F4U had sustained 17 separate bullet impacts during a ground attack mission, yet retained sufficient control authority for carrier landing. Such resilience demanded tactical adjustments that acknowledged American structural advantages while exploiting whatever weaknesses remained. The engineering teams attempted to apply selective Corsair innovations to Japanese aircraft designs, focusing on modifications that could be implemented within existing manufacturing constraints. The mixed material wing construction observed on the captured F4U suggested weight-saving opportunities that might be achievable using simplified techniques. However, even these limited adaptations required precision manufacturing that Japanese factories could no longer guarantee. A proposed modification to the Kawasaki Ki 100's wing design was abandoned when metallurgical analysis revealed that available aluminum alloys lacked the strength characteristics necessary for safe implementation. Pilot training programs incorporated Corsair performance data to prepare Japanese aviators for encounters with aircraft that operated beyond previous experience parameters. The F4U's climb rate of approximately 5,000 feet per minute to 20,000 feet altitude meant that Japanese interceptors had minimal time to achieve favorable positioning before engagement. Training scenarios emphasized the necessity of forcing combat below 10,000 feet, where Japanese fighters like the Ki-100 might retain some performance advantages despite their structural limitations. The captured aircraft's radio equipment had revealed another dimension of American tactical sophistication that Japanese forces could not match but needed to understand. Frequency modulation systems allowed clear communication between aircraft even during high-speed maneuvering, enabling coordination that seemed almost telepathic to Japanese observers. Without access to similar technology, Japanese pilots would need to rely on visual signals and predetermined tactics that assumed degraded communication capabilities throughout combat operations. Lieutenant Toyoda's damage assessment reports provided crucial intelligence for Japanese anti-aircraft gunners, who had been calibrating their weapons based on assumptions about Allied aircraft vulnerability that the Corsair analysis proved incorrect. The F4U's structural design could absorb multiple 20mm cannon hits without losing flight capability, requiring concentration of fire that exceeded most Japanese anti-aircraft positions' coordination capabilities. Gunners needed to understand that individual hits, even from relatively heavy weapons, might not disable approaching American fighters. Factory managers reviewing the Corsair analysis began implementing whatever modifications their facilities could accommodate, focusing on incremental improvements rather than fundamental design changes. One proposed alteration would have strengthened wing spar connections using techniques adapted from American practice, but material shortages forced substitution of lower-grade steel that negated any potential advantages. The gap between optimal design and achievable implementation had become so wide that even minor improvements remained beyond reach. The psychological impact of the analysis extended beyond technical considerations to fundamental questions about Japanese aviation's future viability. Pilots reading intelligence summaries about Corsair capabilities understood that they would face aircraft possessing advantages in speed, climb rate, dive performance, structural durability, and radio coordination. Japanese fighters retained superiority only in specific maneuverability characteristics at low altitudes, advantages that could be negated by American tactical flexibility and superior communication systems. Training facilities incorporated mock combat scenarios based on captured Corsair performance data, but the exercises only reinforced how limited Japanese options had become. Pilots discovered that successful engagements required almost perfect positioning and timing, with minimal margin for error against opponents who could absorb tremendous punishment while delivering devastating counterattacks. The simulated combats often ended with Japanese pilots understanding that survival depended more on avoiding engagement than achieving victory. Intelligence analysts studying broader patterns of American aircraft development recognized that the Corsair represented not an exceptional achievement, but a typical example of United States manufacturing capability. Similar performance characteristics were emerging across the entire spectrum of American military aviation, from twin-engine bombers to single-seat fighters. Japanese industry faced not just the challenge of matching one superior aircraft design, but an entire generation of advanced technology that exceeded their developmental capacity. By June 1945, as Allied bombing intensified and Japanese airfields came under direct attack, the practical applications of Corsair analysis became increasingly academic. Pilots who might have benefited from improved tactics lacked aircraft for training flights. Maintenance crews who understood American design principles could not obtain replacement parts for Japanese fighters. The captured F4U's lessons remained intellectually valuable while becoming operationally irrelevant. The Foreign Technology Section's final recommendations acknowledged the futility of their situation with characteristic Japanese understatement. They could not replicate American manufacturing techniques, could not access necessary materials for significant improvements, and could not implement even minor modifications within the time remaining. The captured Corsair had provided complete technical knowledge, while simultaneously proving that knowledge without implementation capability was essentially worthless. Maintenance manuals were updated to incorporate whatever insights could be applied to existing Japanese aircraft, but these modifications represented cosmetic changes rather than fundamental improvements. Pilots received briefings about American capabilities that served primarily to prepare them psychologically for encounters they were unlikely to survive. Ground crews learned about advanced manufacturing techniques they could observe but never employ. The summer of 1945 brought increasingly desperate attempts to extract some practical value from months of analysis. Prototype modifications were designed and abandoned as material shortages made implementation impossible. Training programs were developed and canceled as fuel shortages prevented flight operations. Intelligence reports were compiled and filed as the strategic situation deteriorated beyond the point where tactical adjustments could influence outcomes. The captured Corsair remained in its Yokosuka hangar, partially disassembled and thoroughly analyzed, serving as a monument to the gap between American industrial capability and Japanese manufacturing reality. Engineers who had spent months documenting its construction returned to their offices to write reports that no one would implement. The aircraft that had promised to reveal American secrets had instead illuminated the extent of Japanese limitations, transforming hope into acknowledgement of insurmountable disadvantage. The surrender announcement reached Yokosuka Naval Arsenal on August 15, 1945, transmitted through static-filled radio broadcasts that crackled across the facility's workshops and hangars. Nomura stood beside the partially disassembled Corsair, its components spread across workbenches that would never again serve their intended purpose. The aircraft that had consumed months of intensive analysis would remain forever incomplete, not because Japanese engineers lacked understanding, but because the war had ended before their knowledge could be transformed into action. Within days of the Emperor's broadcast, American technical intelligence teams began arriving at Japanese facilities to conduct their own investigations. The United States Naval Technical Mission in Japan included specialists who had helped design the very aircraft that Japanese engineers had struggled to comprehend. These men brought with them detailed knowledge of American manufacturing processes, confirming many of the conclusions that Nomura's team had reached through painstaking reverse engineering. Commander Iwaya supervised the transfer of Foreign Technology Section records to American custody, watching as months of meticulous documentation disappeared into Allied archives. The reports that had chronicled Japanese industrial limitations with such devastating precision would become historical curiosities, studied by post-war analysts who sought to understand how technological superiority had influenced the Pacific conflict's outcome. The captured Corsair's analysis represented one of the most comprehensive examinations of American manufacturing capability ever conducted by enemy forces. American investigators reviewing Japanese technical reports expressed surprised respect for the thoroughness of the analysis. Nomura's team had correctly identified structural innovations that even some American engineers had not fully appreciated. Their documentation of manufacturing tolerances, material specifications, and quality control procedures provided insights into American industrial practices that would prove valuable for post-war economic planning. The Japanese had understood American technology with remarkable clarity, while simultaneously recognizing their inability to replicate it. Lieutenant Toyoda's field recovery reports became particularly valuable to American intelligence officers seeking to understand how their aircraft had performed under combat conditions. His documentation of battle damage that failed to disable Corsairs provided confirmation of design decisions that had been based more on engineering intuition than rigorous testing. Japanese observations about American aircraft survivability would influence future military aircraft. Design philosophy, validating approaches that prioritize structural redundancy over weight optimization. The post-war interrogation of Japanese engineers revealed the psychological burden they had carried during the final months of the conflict. Men who had dedicated their careers to aviation technology found themselves documenting their nation's industrial collapse with scientific precision. They had measured every aspect of American superiority while watching their own manufacturing capabilities disintegrate under Allied bombing and resource shortages. The captured Corsair had become a mirror reflecting Japan's technological isolation from global industrial development. American analysts studying Japanese aircraft production records confirmed the accuracy of Nomura's assessments about manufacturing limitations. Japanese factories that had produced hundreds of aircraft monthly during 1942 were delivering fewer than 50 units by the war's end, using construction techniques that had been simplified to accommodate degraded capabilities. The industrial infrastructure necessary for modern aircraft production had essentially ceased to exist by summer 1945. The metallurgical analyses conducted at Yokosuka provided American investigators with unprecedented insight into how resource constraints had affected enemy aircraft design. Japanese engineers had been forced to substitute inferior alloys, accept wider manufacturing tolerances, and eliminate structural redundancies that American designers considered essential for combat survivability. The captured Corsair had revealed not just American technological advantages, but the extent to which Japanese aviation had been compromised by strategic materials shortages. Post-war reconstruction efforts would eventually restore Japanese industrial capability, but the engineers who had analyzed the captured Corsair carried permanent recognition of the gap that had existed during the conflict. Nomura returned to civilian engineering work with intimate knowledge of American manufacturing sophistication that influenced his approach to post-war projects. The precision techniques he had observed in the F4U's construction became benchmarks for quality that Japanese industry would strive to achieve during reconstruction. The captured aircraft itself was eventually transferred to American custody, its components cataloged and stored in facilities that already contained thousands of similar parts. The F4U that had seemed so mysterious to Japanese engineers was, from American perspective, simply another example of routine manufacturing capability. The technological gulf that had seemed insurmountable to Japanese observers represented standard industrial practice for United States factories operating under wartime expansion programs. Historical analysis would later confirm that the Corsair represented more than individual aircraft superiority. It embodied systematic advantages in materials, science, precision manufacturing, quality control, and supply chain management that extended across American industry. Japanese engineers had not failed to understand American technology. They had succeeded too well in documenting capabilities that their nation could not match under any circumstances that existed during the war. The lessons extracted from the captured Corsair would influence post-war Japanese industrial development as the nation rebuilt its manufacturing base with American assistance. Engineers who had studied F4U construction techniques applied similar approaches to civilian aircraft design, automotive manufacturing, and precision machinery production. The knowledge gained through reverse engineering contributed to Japan's eventual emergence as a major industrial power, though this transformation required decades rather than months. The irony was not lost on surviving members of the Foreign Technology section. They had possessed complete technical knowledge of American aircraft design, but lacked the industrial capacity to implement it. Post-war cooperation with American manufacturers provided both the technology transfer and industrial investment necessary to bridge the gap that had seemed insurmountable during wartime conditions. The captured Corsair had revealed problems that could only be solved through fundamental reconstruction of Japan's manufacturing infrastructure. By 1950, Japanese factories were producing aircraft using techniques derived partly from the captured F4U analysis, but implemented with American equipment and materials that had been unavailable during the war. The precision manufacturing that had seemed impossible in 1945 became routine once supply chains were restored and quality control systems rebuilt with Allied assistance. The technological knowledge had always existed. What had been missing was the industrial ecosystem necessary for implementation. The final chapter of the captured Corsair story emerged not through military application, but through peaceful reconstruction. Japanese engineers who had documented their nation's technological limitations with such painful accuracy became leaders in the industrial revival that transformed Japan from defeated enemy to strategic ally. The aircraft that had symbolized insurmountable American advantages eventually became a catalyst for cooperation that benefited both nations. Nomura's detailed reports, preserved in American archives and eventually declassified, provided historians with unique insight into how technological disparity had influenced the Pacific War's outcome. The captured Corsair analysis represented one of the most thorough examinations of industrial capability conducted during World War II, revealing that victory required not just superior weapons, but the manufacturing infrastructure to produce them at scale. The Japanese had learned this lesson with devastating clarity, but too late to influence the war's conclusion.